Learning target number 4. I can differentiate and calculate the difference between harmonics, overtones, octaves, and fundamental wavelengths. Okay? And so first thing we need to be aware of is that relationship. We talked about it a little bit last time. That relationship between pitch and frequency. And they're proportional. That high-pitched sounds have high frequency. Meaning high frequency is lots of wavelengths in a given amount of time. And so it kind of means short wavelengths too. And then low frequency, that would be less wavelengths. Okay, less wavelengths, and so longer wavelengths, and that's lower in frequency. Okay. Now humans tend to hear frequencies as low as 20 hertz and then up as high as 20,000 hertz. And when it's something that is below the 20 hertz range, we call that infrasonic. Sonic means sound, okay? And then if something is above 20,000 hertz, we call that ultrasonic. Compressions and rarefactions. There's a great little video in the slides that shows an animation of this. As sound travels through the air, it pushes these areas of high compression, and that's what propagates through. And then if you watch that video, I really want you to, it's really short, you'll track one individual atom and you'll see that it moves and then it goes back. But the wave itself propagates through the air through areas of high compression and low compression. And these high compression areas are called compressions, and then these areas of low compression are called rarefactions. Okay. If we represent sound wave with a transverse wave image, then what do the peaks and the trough represent? Okay, so here is our sound wave, right? And then we have this transverse wave that's representing the sound wave. So let's look at this. The troughs are lining up with our rarefactions, and our peaks are lining up with our compressions. Okay, so the higher the compression of these air particles, the higher the amplitude. Okay, and so that's what I want us to keep in mind. And those compressions, how compressed those air molecules are, particles, molecules, whatever is in the air that we're working with, that is directly related to loudness. So the greater the compression, the greater the loudness, which would mean if we're talking about this transverse wave here, the greater the amplitude is greater loudness. Okay. Now these are sound waves, and so that means they travel the same speed. So if these are all the same distances, that means these waves all occurred in the same amount of time. All right. So each wave to the right is a sound wave traveling through air. Which sound or sounds are the loudest? So we just talked about that being the highest amplitude, which would be the greatest compression. So when I look at amplitudes here, it appears that A and D, from our origin, have the similar or the same amplitudes, which is greater than C or B. Okay, and so which ones are the loudest? A and D, because their amplitudes are the greatest. Which sounds have the highest pitch? Well, highest pitch means highest frequencies, so more waves in a given amount of time. And so when I look at each of these, peak to peak, so 1, 2, 3, 4, 5, 6, 7-ish wavelengths, 7.5, and then 1, 2, 3, 4 wavelengths, 1, 2, 2-ish wavelengths, 1, 2, 3-ish wavelengths, okay? And so we can visually look at this and say, if this is a sound wave and they're traveling the same distance, and this happened in the same amount of time, and so that has the most waves per time frame, so this would be my highest frequency. So which sound or sounds has the highest pitch? That would be A, because it has the highest frequency, and frequency and pitch are proportional. We measure loudness in decibels. Decibels are really interesting. Each decibel means that there's a sound intensity of 10. Okay, or sorry, each 10 decibels. So if we increase from 20 decibels, it would be 10 not to the first, but 10 to the second. And so we'd have a sound intensity of 10 multiplied by 10, or 100 times greater than it was before. Okay? So example problem number 6. How much louder is 50 decibels than 20 decibels? Where there's an increase in decibels of 30, right? And that correlates to a sound intensity of times by 10 to the third. Okay. 10 times by 10 times by 10. Yeah, 1,000. So the new sound is 1,000 times louder. And then I like this slide just kind of give you a connection to things that you might be familiar with as far as decibel level. Okay. Oh gosh, sorry. Now, oh, this isn't perfectly. Know that each of these comes to like a point like this, okay? All right, so if this is like a guitar string, or if it is a transverse wave representing a sound wave, but I like thinking of this as like a stringed instrument, and it absolutely works for these stringed instruments. If we have a guitar string, and this is the standing wave that's produced, okay, where we do not have any nodes in the middle there, we call this n equals 1, and there's all these different names, okay? So first, this is the fundamental. We don't call it an overtone yet. Overtone will start here. So n equals 1, it's a fundamental. We also call it the first partial or the first harmonic, and the number of nodes, excluding the ends here, is 0. Okay, we don't have any nodes. For n equals 2, we call this the first overtone above the fundamental. It's the second partial, and it's the second harmonic, and it contains 1 note. Okay? And then we follow this pattern. You need to be familiar with the differences here. And like an example of something you might see on the test. I might say, how many nodes does an n equal 3 wave have? And you need to recognize that an n equals 3 has 2 nodes. Okay, so let's start drawing some connections here. The n number correlates to the partials, right? So if n equals 3, that's the third partial and the third harmonic. The number of nodes correlates to the overtones. So if it's the second overtone, then it has 2 nodes. And then the number of nodes in the overtones is 1 less than the other values in our n number. Okay, this is a nice little diagram here that just tells you the frequency of different notes, okay, from any instrument. And then if you play an instrument, especially the piano, you're probably really familiar with middle C, and that's just C4, and it has a frequency in hertz of 261.6, okay, hertz. So let's add something here. Let's try something out. what is the wavelength of middle C? Okay, we know the frequency. We know frequency from this table, it's 261.6 hertz. And we know that the velocity of the wave, because it's a sound wave in air, 343 meters per second. And we have an equation, velocity equals frequency times by wavelength. So if I want to solve for wavelength, I'll divide by frequency. So velocity divided by frequency equals wavelength. 343 divided by 261.6. And so this would be 1.31 meters. All right, two equations to be familiar with. Harmonic frequency, if we want to figure out the frequency of a harmonic. Okay. So if we want to figure out the frequency of a harmonic compared to a fundamental, we're going to take the frequency of the fundamental and multiply it by the number of harmonics. Okay, so that one's pretty simple. If we want to figure out the frequency of an octave, okay, let's look back at this table. If you're not as familiar with music, music goes note-wise, C, D, E, F, G, A, B, and then it goes back to C again. And so if we're going from a C to another C to another C, these are all octaves, okay? So if this is middle C, this would be an octave above middle C, that would be 2 octaves above middle C. And so if we want to figure out that frequency of an octave, you're going to take the fundamental frequency multiplied by 2 raised to the number of octaves that we want to move.